That hair becomes like that was actually good. Left it in soft. Okay.
It's an apple sauce.
Was that the food?
I don't know. Say again.
Stop that for me. Stop recording.
French fries.
It's so hot. It's so hot. It's so hot. You've never been hotter.
Part 3.
Oh, this is the last thing. It's never fucking good. I don't eat that.
You have to favorite that one and then watch it. I'm pleased. You're gonna get to do something. Hey, we need to do something together. Like that. Let's do something. It's not this week, but next week. I think.
Next week, sure.
Bye. Yeah.
We have inverted. Unfortunately, come back and forth. So there's not so small. It's we're now showing the lives. Well, yes, we can have them up. Yeah, they are. Oh, actually, wait, one second. Oh no, nobody's sitting there, but I found that one. I was supposed to get very specific. Thursday. I remember being. I checked on the watch. Yeah. There. Are you dating? Oh. Oh, okay. Good. Did you really? I like, oh, you see this? I remember that. I like. So many things. Oh, really good. And also I had it.
You got the details?
But he's like, oh, like, come up and see it.
Okay, let's start. We're running a little behind. So we're going to wrap up on work today and move on into potential energy. Let's start with this problem. And I've drawn a slightly blown up version over here. If you need it. I have a hockey puck. It's an overhead view. So it's just sliding on the horizontal ground. Well, horizontalized, frictionless, and in two different cases, before and after velocities. And we need to rank the situations according to the magnitude of the work. Oh, and does anyone, I printed some new ones. Okay, 1, 2, all right. Anyone else? Oh, yes. We'll stop by the consumer. It's fine, it's fine. Okay. Anyone need more time? Bit more time, all right. I'll give you one hint. You don't know enough about the force. All right, get ready. And show me what you got. Okay, we've got a variety of answers. Go ahead and discuss.
Sure.
Oh, yes, okay, yes, good, yeah, so remember that you're squaring the ends of factors. Don't subtract them. Okay, so we
And now can I
We'll go. Yeah.
This one should be.
You just need one person.
But like this one, like I.
It's not sure, like.
Oh, I think it's because
Three and one. They're both less than what you
I guess. That's so one actually.
Okay, so you're squaring it negative.
And this thing is going that way.
Look at pairs 1 and 3, they're both just taking 10 to 11. Right? Yeah.
You were saying it doesn't.
I'm gonna say, I might be offended by that. Yeah, we have these guys, C squared or the.
How do you calculate the change?
So you see what just like one half.
The shade of the same here.
So the final square minus. Yeah, okay. How much is it for
11 squared. So it's squared, they're all the same. Oh, actually, I don't know.
One changing method, you method so we do the same method.
Surprising.
Wait.
That was unexpected.
Okay,
I just think.
all right, get ready and show me what you think. Okay, it's mostly for E. E is correct, they are actually all equal. Yes, it's great. We don't have enough information on the force, and it's the only, but the applied force is the only force doing work, so we can use work total equals change in kinetic energy. So we just need to compare the kinetic energies before and after. It's identical hockey pucks throughout, so the mass is the same, so we can sort of ignore the mass. We're going to look at V final squared minus V initial squared. So here you have 11 squared minus 10 squared, right? So it's 121 minus 100 is 21, right? Here, same thing, 11 squared minus 10 squared, 121 minus 100, 21. What do we have here? 5 squared minus 2 squared, that's 25 minus 4 is again 21. All right, and so all three of these cases have the same amount of total work done. Questions? Yes.
Is that something like we're able, like, to get the total work, we can just base it off of like initial and final velocities?
Remember that we had the work energy theorem. Told us that the work total is the change in kinetic energy. And kinetic energy is 1/2 mv squared. So we have 1/2 mv final squared minus 1/2 mv initial squared. Yeah, okay. Other questions? Yes.
I'm just a little confused on like the angle of these two and like since it's an overhead view where the force is like parallel to the ground, like did that just like not play a role in this scenario?
Yeah, it doesn't end up playing a role, yeah. Now I'll sort of bring up one of the most common questions I get is, wait, how can 1 and 3 have the same work done? Surely it's much easier to just like speed this up in this direction compared to like completely reversing the direction over here. Thing to remember is that work can be both positive or negative, right? You're right that it is easy to speed this up, right? So to speed this up, I just need to push in the same direction that it's going, and I'll be increasing its kinetic energy, so that's going to be doing positive work. Here, what happens? I first need to slow this down to 0. During that time, I'll be doing negative work. Then I need to speed it up from 0 to 11. During that time, I'll be doing positive work. And the total work, right, the sum of that negative work plus that positive work, that total work will be the same as in that case. Questions? Yes?
I want to know why direction of velocity doesn't matter.
Because kinetic energy is a scalar quantity. So when we do v squared, right, we just need the magnitude of the velocity vector squared. I know that might not be a very satisfactory answer, but yeah, kinetic energy, yeah, it's a scalar quantity, doesn't have a direction. Other questions? Okay, in that case, let's talk about this. Alright, so the setup, we have a mass attached to this pulley. This pulley is a free pulley, just supported by the rope. That rope goes like that. And you're pulling on this end. And yeah, you pull down 10 centimeters, and the question is about how much work you've done. I'll give you another 20 seconds. Right. And remember, if you're totally confused, it's fine to like, just show me everything. And that's, that's also feedback. All right, show me what you think. Okay. All right. We've got a variety of answers. I'll give you a couple of hints before we go to discussion. If I instead ask for the total work done on the canister, what would you say? 0, right? Because it starts at rest and ends at rest. But the question is asking for the work that you do. So obviously you must be one of the things contributing to the total work. All right, so we have work total equals delta K. So that's going to be equal to 0. You're one of the things doing work. What is the other thing doing work? Gravity, yes. Oh, I heard someone say tension. Depending upon how you choose your system, yes, you could say tension is doing work. But I'm going to choose my system to be the rope and the canister and this pulley. So then tension is an internal force, so it's not going to do any work. Yeah. Okay, so we have these two. Now, directly trying to calculate the work done by you actually can be a little tricky because the force that you exert is actually going to change with time, because initially, like to hold it steady, you need one amount of force, but to get it started in motion, then you need to increase the force a little bit, right? And then it's moving, and then to like let it come to a stop, you need to decrease the force a little bit. So it's like actually a time varying force that you're exerting. So it gets a little complicated if you want to accurately calculate that. Right? But work done by gravity should be much easier to calculate because that's a nice constant force, right? And as long as we can find that, then we can figure out what the work done by you is. So yeah, so I'm going to throw it to discussion. I want you to first figure out the work done by gravity, then use that to figure out the work done by you. And my other hint is think about how far the canister moves. All right, go ahead and discuss.
I think it could be automatic. Well,
Yeah, because it's almost
we should put it in 0.1 meter.
eventually.
Then we know. And we'll see what happens.
Yeah, well, I mean, actually, let's do this first. It's your work.
That's a lot.
So,
Because you Everybody else should share that. I said negative two about it. Changes the pattern. So this is. I just have like. No, I didn't. My work is fine.
That makes sense.
Okay. Sorry, I know I'm rushing you a little bit. Okay. You guys ready? And. Okay, mostly for CC is correct. Okay. So, let's. Yeah, let's think about this. So we're trying to find the work done by gravity. Gravity is a nice constant force. So we can say work done by gravity is going to be just F grav dot delta R. The F grav here is minus mg j hat, right? Mg magnitude in the negative j hat direction. I'm assuming upward is plus y. And the delta R, it's also moving just in the y direction, and it's moving, we can say it's y final j hat minus y initial j hat. J dot j is 1, right? So then this will simplify to just minus mg times y final minus y initial. And we can see that, well, y final is greater than y initial. So this will be positive here, but then you have a minus sign here. So overall, the work done by gravity will be negative, which makes sense. It's moving upward, but the force of gravity is downward. They're in opposite directions. So the work done by gravity will be negative. Sorry, yes. Move the monitor. Right. You could just change your seat. Okay. All right. So that's the work done by gravity. We know the mass, 12 kilograms. We know G, 10. So 120 newtons is the force. How much distance does the canister move? 5 centimeters, 0.05 meters. Any questions about that? Is everyone okay with the fact that, yes, yeah.
Why do you know it moves 5 centimeters?
Why do we know it moves 5 centimeters? Yes. Let me sort of help you visualize it a different way. If I were to, without touching the rope, just directly move this pulley up by 5 centimeters, right? I would have some slack, right? But I would have like 5 centimeters slack here and 5 centimeters slack here. So then when I pull this rope to make it taut again, I have pulled it down 10 centimeters. Okay, so the canister only moves 5 centimeters, and so we can calculate, and the work done by gravity will be -6 joules, and so then the work done by you must be the negative of that, so positive 6 joules. Questions so far? Yes.
So the force done by the person is acting in the downward direction.
Yes.
So why isn't the work negative?
Oh, I see.
Because it goes upwards.
Right. The force done by the person, yes, but the person is not directly acting on the mass, right? The person is acting on the end of the rope, and the rope end is moving downward. Yeah. That actually brings up another interesting thing, which is there is, if you make some very broad approximations, you can sort of directly calculate the work done by you. Now, yeah, so supposing we were just holding this steady, we weren't moving it down, we were just holding it steady. This is 120 newtons of force pulling down. What is the tension in the rope? 60, right? Because you can see this pulley is like, oh, 120 down, 60 is 60 up, right? So the tension in the rope is 60 newtons, which means that, oh, you only need to exert 60 newtons to hold it steady, right? Now, as we said, when you actually pull it, you have to bring it into motion and then slow it down. So sometimes you'll actually be exerting more than 60, sometimes less than 60, but on average, you'll be exerting 60 newtons of force. So you could say, oh, 60 newtons of force, and I'm moving in 10 centimeters, right, 0.1 meters. So that's again 6 joules. Right? And they're both in the same direction, so positive. Yes?
So why final minus y initial turns out to be negative to make it positive?
No. This was
Oh, it's okay.
yeah, work done by gravity is negative,
Yeah.
and then work done by u is positive. So yeah, so you could sort of directly calculate the work done by you by saying that you're on average exerting 60 newtons and moving in 10 centimeters, and you're pulling downward and the rope is moving downward, so that's positive 6 joules of work. So we see the trade-off here. You had to pull the rope 10 centimeters in order to raise the canister 5 centimeters, but the advantage was you only needed to exert 60 newtons of force compared to the 120 if you try to pull it directly. And so that's what all the simple machines do, is do a trade-off. Usually what they do is they decrease the amount of force you need to apply, but increase the distance that you need to apply it over. Like even a ramp, basically what you're doing is, in order to raise a heavy object by some vertical height, you need to push it a very long horizontal distance, but you're not directly working against gravity, you're just pushing it sideways, and the normal force is what's actually sort of lifting it up as you move along the ramp. So yeah, so simple machines are cool that way. This amount of work done is still the same, but you can be less tired because you're exerting less force. And we have a demo. I'm going to need, actually Frida, would you like to? Thank you. All right, so hold this for a second. All right, so first we'll have it in the simplest way possible. Okay, so what I want you to do is, yes, put this hook, yep, exactly, and then hook the other end of that over there. Yeah. Fantastic, thank you. Yes, and actually we'll move it to okay, and then I'll put it up and just make sure that this isn't banging against. Yeah, okay, yeah, okay. All right, so cool. So in this case, the pulley is not really doing much. All it's doing is redirecting my force, right? It's not helping me in any way. And so you can see that the weight is 57, sorry, in case you can't see that, about 57 newtons. Okay, all right. But let me now rearrange our system. Thanks. And if you could actually attach that there. And let's see what would be the best way. Yes, okay. Yeah, if you could just hook that on there. Does it fit?
No.
Not really? Okay, then we can do another end. Yeah. Okay, thanks. Should have done it from the other side. I'll do it from this side. Okay. Okay, so now this pulley is just supported by the ropes, right? But there are 2 ropes now supporting that pulley. And so when I lift it, you can see, yeah, it's much less than 55. It's not exactly half because the rope does have a mass here. It's not a massless rope, but you can see it's definitely a lot less. So yeah, that's the mechanical advantage of this. I think they call this a pulley of the second kind. The other one was a pulley of the first kind. But yeah. To figure it out. All right. I think that ties up work. Oh, okay. One last definition that I forgot to give you, which is about power. I'm not going to ask you to do this problem right now, but do take a look at it later. Yeah. Actually, yeah, I'll just. So we know that the base definition of work is integral f dot dr, and we said that the integral is like a sum of, like, you take your part, you chop it up into lots of tiny pieces, you find the work done for each tiny piece, and you add them all up. But supposing you didn't do that, supposing you just took a tiny piece of displacement, then you would be doing a tiny piece of work. That's what we think of this d as, really. We think of it as like, oh, a tiny piece. And so tiny piece of work, if you just have a force acting for a tiny displacement dr. But then you could talk about the rate of doing work. Right? So dw over dt, so that becomes f dot dr over dt. What is dr over dt? Velocity, yes, rate of change of position, that's velocity. And so that's f dot v. And this is called power, or instantaneous power. Well, I guess, yeah, we'll just say it's power. If your v is average velocity, then it's average power. If it's an instantaneous velocity, then it's instantaneous power. The units of power, we can see that, okay, it's work over time, so it's joules per second, right? Somewhat unfortunately, that has the name of Watt. Okay, named after James Watt, who didn't invent the steam engine, but he improved its efficiency. And unfortunately, the symbol for a watt is capital W, which is very confusing because you use a watt to measure power, which is not the same as work, which we also often denote with a capital W. So, check the context to see what W they're talking about. We are well on the way to running out of the 26 letters of the alphabet. That's why we'll eventually, especially in 116, start to use Greek letters a lot. Yeah. Mathematics has already gone like beyond Greek letters. We're like, oh yeah, Hebrew letters. Yeah, let's do it. Okay. All right. So that sort of wraps up the work and work energy theorem a little bit. But we're going to actually transition into potential energy and so on. And so we mentioned before that conservative forces, that one of the things that's special about conservative forces is that the work done by conservative force, as you take the object along a path, the work done is path independent. It only depends upon where you start and where you end, right? Another thing about conservative forces, let's say each conservative force has an associated potential energy. And the traditional letter for that is U. And we will define something called mechanical energy. And so it's E mech, and that's going to be kinetic energy plus potential energy. And we'll see later why that's a useful combination. All right, but we haven't really defined potential energy, right? We just said, okay, you can associate some potential energy with the conservative force. How do we define it? I'm going to erase this part of the F dot V bit. Is that okay? Oh, all right. All right, so the way we are going to define potential energy is through work. We're going to say that the work done by a conservative force is negative delta U of that conservative force. All right, I know this is a little confusing, but basically it's like depending upon the force. So if the conservative force you're dealing with is gravity, then you would say, oh, work done by gravity is negative delta U gravity. In this course, the main conservative forces we'll be seeing are the gravitational force and the spring force. But there are plenty of others. Once we go to 116, electrostatic force is conservative force. Yeah. All right, so we're going to use this relation to define potential energy. So let's see it for the case of gravity. So I need the work done by gravity. And I want a completely general expression. So we'll start with F of dr, but this F has to be then force of gravity if I'm looking for the work done by gravity. And the force of gravity is minus mg j hat. And dr, remember, is dx I hat plus dy j hat plus dz k hat, but just to save time, I'm going to drop that off. It's going to disappear anyhow. Integral is still here. All right, but what is j dot I? 0, and j dot j? 1. So this simplifies to minus mg dy. Integral from initial to final. And m and g are constants, so I can pull them out. So I get integral dy from, I can specifically say y initial to y final. The integral dy is just y. I have y evaluated at y final and y initial. So let me just summarize that up here. So I get work done by gravity is minus mg times y final minus y initial. And I'm just going to distribute the mg inside. I'm going to leave the minus sign outside. So I have mg y final minus mg y initial. Any questions? So far, I've just been calculating work. We'll bring potential energy in a moment. So any questions about these steps? Okay. Any questions? Charles? Yes. Good. All right. So we have that. But we said that by definition, work gravity should be equal to negative delta U gravity. But delta, we know we are always defining as like final minus initial. So this should be minus, and then we have U gravity final minus U gravity initial. So if I compare these, what do I see? I see that, oh, I can get an expression for U gravity, which is mgy. Yes.
Where does the dx I have? Oh, it's 0.
Good. Yes.
Yeah, I'm a little confused about the last step.
Oh, so I'm just comparing this expression with this expression, right? And so then it's like, oh, the minus is outside, parentheses, and I have like some final term minus some initial term, some final term minus some initial term. So if I'm saying that by definition that these are equivalent, then it makes sense that like, oh, this should map onto this, right?
Oh.
And so then if I sort of generalize, it's like, oh, okay, if I don't restrict myself to like final and initial, then it just becomes some general height y.
Okay.
Also, I realize since I don't need this anymore, I'm gonna move it out of the way. Yes.
So that UGF term, is that like the final, like, potential energy of gravity? Is that kind of like how you should look at that?
The final gravitational potential energy of the object that that is being worked on by gravity.
So it's not like you're like multiplying by G or anything,
By G.
because there's like the G term, so you're not like multiplying by like G, like after the U, there's like a G. So do you?
Oh, no, that's a subscript. Sorry,
Okay,
yeah, the G and F here are subscripts. Yeah, yes.
Alright.
Yeah, if you want, you can make that more. You grav final and you grav. Other questions? Yes, yeah.
For y in the final equation.
Yeah.
Like, how does that work? Like, how does that come in? I'm confused on that.
No, so we're just sort of comparing these two, right? And we say that, okay, we have some final term here, we have some final term here, so then, you know, if this is sort of by definition, these two things are equal to each other, then it makes sense that, oh, U graph final is MGY final, and U graph initial is MGY initial. And so then I'm sort of generalizing to like, okay, let me just say it for any general height Y is MGY is U graph. U graph of Y, if you like, it's a function of Y. Okay, now technically, of course, I've sort of cheated a little bit because actually this could be MGY plus some constant C. Because if I use that over here, I would get like MGY final plus C, and then minus MGY initial, and then there's the plus C term, but the C's would cancel out when you subtract them, right? And so that doesn't really affect things very much. We sort of traditionally set it to 0, but there's still an ambiguity here, which is this is a function of Y, but Y according to who? Right? And right, because the value that you get for the Y coordinate depends upon where you set your origin, and different people can set their origin in different places. So, for example, with this block, I could put it here. I could put it there, and it could be that, for example, I say that, oh, I'm going to set Y equals 0 here, whereas maybe Julia would say that Y equals 0 on the floor. Okay, so then for me, let's say this is about a meter. I would say, oh, when I'm calculating the gravitational potential energy, it would be mass of the block times G times the height of 1 meter. Whereas Julie would say, no, it's mass of the block times G times the height of about 2 meters instead. So we would get different answers for our U gravitational, and that is okay. Why is that okay? Because we never directly measure U gravitational. What we observe are the changes in potential energy. Because it's whatever potential energy you lose or gain that's going to affect how much your kinetic energy is going to gain or lose. And so if I'm talking about a process, say taking this block from here to here, the change in Y is the same for both of us, right? I describe it as going from 1 meter to 0 meters. Julia would describe it as going from 2 meters to 1 meter, but the change is the same. So the change in potential energy is the same for both of us. And that's all that really counts. So in problems when you're using gravitational potential energy, make explicit where you are setting your Y equals 0, because different people will have different choices. Questions? All right, so we saw one conservative force, which was gravity. Let's look at another one very quickly, which is the spring force. And so the spring force is also conservative force. So again, we have a similar equation. The work done by the spring is negative delta U spring. So I'm going to modify its calculation and adapt it to the spring. So instead of grav, I have SP. So I'm going to need the spring force as a vector. So to make life simple, I'm going to set up a specific scenario. So say this is a wall, we have a spring, and this is the end of the spring. And we're going to say that when the length is the natural length of L0, right, unstretched length, that the position of this end of the spring is x equals 0. And then I'm going to stretch the spring. Right, so this is the new position. And so since I've displaced it away from the origin along the x direction, let me just call that x. Distance from the origin along the x direction. So this is some new length L. We know that the magnitude of the spring force is K times S, where S is the absolute value of L minus L naught. In this case, what is S? Just X, right? Okay, so that's easy enough. But if I want a vector form for the force of the spring, so okay, the magnitude in this case is Kx, but what direction is the spring exerting force? Yeah, it's pulling it back. It's trying to bring it back to its natural length. So that would be in the minus I hat direction. Okay, so that's my spring force as a vector. All right, so then I'll stick that in here. So I have minus Kx I hat, and then dotted with dx I hat plus dy j hat. Now I do the dot product, but now I'm doing I dot I is 1, I dot j is 0. So this will simplify to just minus kx dx integrated from x initial to x final. K is a constant, I can pull that out. So then I have integral x dx from x initial to x final. And that will give me x squared over 2 evaluated at x final and x initial. And so I get minus 1/2. Yeah, okay, I'll put a parentheses there. So the minus is outside the parentheses. You have 1/2 k x final squared minus 1/2 k x initial squared. So this is the work done by the spring. But if possible, I want to make this, I don't want to have to set my origin at, the unstretched length every time. I want to have the freedom to put my origin wherever I want. The x here, what it represents really is the stretch, right? So I can replace that. Now that I'm squaring it, I don't have to worry about x being positive or negative. I can just replace that x with an s. So I have minus 1/2 k s final squared minus 1/2 k s initial squared. And once again, I'm going to say, oh, well, this should be equal to negative U spring final minus U spring initial. So if I compare these, what do I get for U spring? Yes, 1/2 Ks. Oh, question.
So the S is like literally the change, right?
Yes, it is the change from the natural length, yes.
So when you're looking at like, you substitute like initial and then final.
Yep.
Those are just stable. So it would be the change, that would just be like where it's right.
No, that would still be the change. It's like, so I call it the stretch, but it could be equally compression. It's the change from the natural length, right? So maybe the natural length of the spring is 10 centimeters. And maybe your initial stretch, you initially stretch it by 2 centimeters. You bring it to total length to 12 centimeters, right? So it's initial stretch of 2. And then you maybe stretch it some more until it's 15 centimeters. So then the final stretch would be 5.
So like the initial is not necessarily the natural.
Correct, yes, yeah. S initial is referring to the initial stretch, which could be different from 0. So the length could be different from the natural. Yes, Danny.
I'm not looking for that question, but why not just say that S from like from the start, as opposed to changing it as twice the length to FS?
No, that's a reasonable question. It was just to make this dot product simpler, honestly,
Okay.
because I want to get everything in terms of one variable, in this case x, so that I can do the integral.
So since X is basically X, that's why you can plug it in the problem.
Yeah.
Okay.
Other questions? Okay, we have 3 minutes left. So I'll take you through an example of using the conservation of energy. All right, I'm going to erase the board. All right, so let's say this problem is on the slides, but I don't want to bring the screen down and all that. It will take more time. So I'll just lay out roughly what the problem is. So we have a frictionless floor that transitions to a ramp at 30 degrees. We have a wall, there's a spring attached to it, and then there's a mass. And what we do is we push the mass up against the spring and compress it. The initial compression is known, and then we release it. And the spring pushes it away, and the mass is not attached to the spring, it's just pushed by the spring, slides across the frictionless floor, and then up the ramp. And the question is about finding what is the final height that it reaches. And we know the spring constant, and we know how much it was compressed initially. All right, so what does the word conservation mean?
Nothing is lost.
Nothing is lost. Yeah, you can talk about conservation of nature, right? You're trying to preserve nature. So conservation of energy, similarly, you're talking about energy not being lost. So in this case, we're talking about mechanical energy not being lost. So we're going to use the idea that the initial mechanical energy is going to be equal to the final mechanical energy. But in order to do that, I need to define when is my initial moment and when is my final moment. So I'm going to choose my initial moment to be spring compressed and block has just been released. And my final moment will be, it's gone up the ramp and it just comes to rest. So the block has come to rest. All right. So we said previously, I've erased it now, that E mechanical is kinetic energy plus potential energy. Here there are two possible two relevant potential energies, the spring potential energy and gravitational potential energy. So I'll have K initial plus UG initial plus U spring initial equals K final plus UG final plus U spring final. And then I can plug in my general expressions. So K is 1/2 mv squared, so that's 1/2 mv initial squared. UG is mgy, so that's mgy initial. And then you have 1/2 Ks initial squared. Similarly over here. All right, but with these choices of initial and final, several of these quantities are going to be zero. So just call out like zero or non-zero. So K initial,
Zero.
zero, blocks at rest. UG initial,
Zero.
zero if we choose this to be our zero height, right? Which is sort of the natural choice, but it's good to make it explicit. So we'll say that, yeah, y equals zero on tape. All right, U spring initial, zero, non-zero? Non-zero, okay. K final,
Zero.
zero comes to rest on the slope. UG final, non-zero, non-zero height from the table. And U spring final, zero. The spring is no longer compressed and will have relaxed to its natural length. So I'll just mark some of them as zero. And so what we're left with is just 1/2 K S initial squared equals mg y final. And we're trying to find y final, which is h. So we can say h equals y final, which is simply going to be K S initial squared divided by 2mg. And these are all quantities that were given to you. And so we got it. All right, so just to recap the sort of things to keep in mind, set up your scenario, choose your initial moment and your final moment. Make sure there are no non-conservative forces. If there are non-conservative forces like friction acting, then you can't use conservation of energy. And then like lay out all the individual expressions, see which ones are zero, so on. All right, we'll get some practice with this on Friday. I'll probably also post a video for you to watch about the connection between energy conservation and the work energy flow. And pick up your folders if you haven't. You too. You too. Hope you feel better. Yeah. Is that empty? Shall I pass you? Okay.
One of it's that I was using.
Oh.
Yeah.
Oh, I forgot to do this thing. I don't remember off the top of my head, but you know that if you get less than a 4, that means
Okay, so they're all.
almost 4. You should know this by now.
Okay. I'm confused why I got this. The skate that I was looking for original.
Oh, they probably didn't see that. Yeah. So.
This is the only point I got.
That's correct. Okay, no, that's fine. I mean, I would have also just put in like in symbols as well, just the step showing you.
Oh, I did, it's, wait, I didn't put in the symbol of adding them.
Right, yeah, but, yeah, let's, yeah.
One's having like.
So this is for the.
Yes.
So they wrote like in
Wait, so is this, no, this is problem 5. This is the book being pushed up the ramp.
Oh, it's like, wait.
There's no normal for this one.
Are you in that?
Okay.
Finished A of the challenge. I have a little bit of shit.
Anyway,
I think I'm.
Yeah, it's this one. Yeah.
yeah,
And then just whatever else.
So, I thought
Yeah, it's
it would have been 0.
exactly, yeah.
So, and I gotta,
Yeah, it was close enough that, yeah, you don't have to redo it, but yeah, it is actually, because it is close to. You didn't need to do all of that, yeah. I mean, it's basically, it's like if you did the other way of doing the dot product, where you just do like magnitude times cosine theta, then it would directly get to 0.
I don't want to say.
okay. Now I have to figure out what went off.
Those are on the tape though.
It was just like.
Someone from the past.
What problem did you do?
No, so remember the subpart is out of 4. So anywhere you didn't get 4, that means you're correct. Yeah, you need to, well, just explain your reasoning a bit more using your free body diagram, like how you know. Like, some of them is just obvious, like it's told in the question that like, oh, this stays constant or this changes. Some of them are like, oh, like you can say that, oh, because F applied increased in part 2, that's how you know that Fn should increase, stuff like that. So just like write it out a little bit. Yes, yeah, just the correct partial correction, but I mean, as in include the original and then just rewrite the partial correction.
Yeah, you go first.
Oh, yeah, I did my little stuff.
Okay.
Pressing customer.
Yeah, I don't get why it's.
I don't know why.
Oh.
Yeah.
Oh,
We have present spring, we just released the
So, you know, I went to
spring, so
Wendy's
it's starting from 0 velocity and then speeding up as the
And
spring.
I have the Krabby Patties. You should check out my vlogs.
Which, okay.
Oh, cause you can't. Video.
No, like I think it's like a little bit of that. But like the thing is, like,
Either way.
which one?
That'll be
Like,
Yeah,
check what the players.
No, it doesn't start with high
Yes,
velocity.
I did say.
It starts with high acceleration, but the velocity is starting from 0.
Or it's just of the youth having there. The third one.
It was really hard. I told you how fun it was.
Oh.
For what?
For
Oh,
what?
it was so.
It's the same, okay. Because
Cause like you're supposed to be pineapple flavor too.
So none of us like fully get questions, or you got questions, or something?
T1 will not be equal to T2.
that's what she wrote that on.
Yeah, if you do that, you're gonna.
I got that, this
Really? That's what they wrote down?
T1 is not equal to T2, right?
No, it does not.
Yeah.
Um,
Cause one has rapid, like they have.
yeah, no, these aren't the same expression. One of them has a minus sign.
Oh, one is a minus.
But other than that.
They're very similar, yes.
They're very similar, but other than.
Well, yeah, what's the question? Okay.
So what would you?
Oh, energy plus E squared over.
That should really get cut off.
Well, I mean, as in that way, he starts, we're showing him in the middle of motion. He starts at the top.
So it's literally just.
Pause. What is that?
Yeah,
Why would you do cheeseburger and then dessert?
Literally in the first slide.
Well, so technically I would fries in the.
Okay, I guess that's real.
Yeah.
You can't do cheeseburger. He's not.
Oh, yeah, talk further during office hours if you can come
I
out.
would, I would.
I
Today
forgot I
was
worked.
2:30 to 4.
Yeah, but I still wanted to.
Hello. Hi, my number. I like, for some reason it's like, all my pages are missing except for this one.
Oh, no.
All my work for this stuff like didn't get checked,
yeah.
so like my review,
Wow.
I guess I just don't, like I already did the work, but
So you just need to print it, right?
yeah. Right, but okay.
Oh, okay, I can check the numbers for you.
No, I was just sitting in Spanish, like doing Spanish. I think there was like 70.
Yeah.
Which one is 1, 2, 3?
No, I was in silence laughing by myself in this deck chair. I thought it was so funny. I was like, oh.
Oh yeah, this middle.
I mean, like last time there was like
Wrong
100.
one, so
Last
I
year
said
was
like
so
this.
funny. I think that's today, like legit during my 950.
Okay,
there were,
yeah.
like,
This,
seven-
so I mean, I would suggest when you reprint it, right, just
I
make
wanna
sure
get
you
your-
label the strings
so you
also,
have
just
this.
like.
Okay,
No,
yeah,
I-
that's
What is this picture making? How does it make
okay, thank you.
honest thought?
Yeah, well, I
It's
did
making-
technically forget to do this for the second section, but
Because like
You
it gives like
remember
little
what-
like otherworldly vibes.
Oh, I
I feel like
Wednesday, which you have.
Yeah, no, Wednesday I'm here.
Now read
Okay.
this top to bottom.
Thursday forward.
Okay.
But I think got the air track on today.
Yes,
And I think there's something else, but I don't know what it is.
Yeah.
Yeah.
Right. Yeah, no,
Yeah.
don't worry about being this market.
Okay.
So this was,
Yeah.
this was easy.
So fully went for.
Good.
Yeah,
Wonderful,
yeah, I had a student help me with the like holding things out while, yeah.
perfect.
Oh.
Thanks for your
Well,
there.
if you wanna go to the file, I mean,
What is it now?
that is not how
Thank you.
So yeah, sorry, the what is not here?
That's not mine.
Oh, the
It's just,
bottle? Oh, I'm just gonna leave with you.
Okay.
All right.
And next question, I know in like the Macmillan.
Yes.
Like, they talk a lot about like the potential energy, usually, it's like law of like universal gravitation.
Yes, yes.
Are we gonna do that derivation as well?
No.
Okay.
Yeah.
that's real.
So that is sort of just for your education. You don't have to worry about it, won't be on the exams, but it's good to see it.
Because that one would make me a couple of it.
Okay.
I can tell you.
It's good, like, if you have time, look through it, because there'll be a similar one in 116. So, yeah, it's good to be able to follow along the steps. But yeah, it's not an urgent thing, so,
Right.
yeah,
But if we can't follow along and stuff, that's not like the end of the world.
it's not the end of the world.
Okay, that's real.
Yes.
Mine was just about the, I don't know if you wanted me to talk about it now or like during office hours later today.
I mean, if you have time during office hours, then let's do that, because I need to go to a meeting soon.
Yeah, so that's fair.
Okay, great, thanks.
See you later.
Yep.
Thank you so much.
Yep, see ya.